Alright, welcome students to the Mike Sod Academy. So we are going to be looking at the Hall effect today. So what is the Hall effect? The Hall effect is an effect that helps us to dictate charge carriers. So Hall was able to dictate the size of a charge, if the charge is going to be positive or negative, using this word Hall effect experiment. So in this experiment, what he did was to place two conductors with different charges. So the first charge here is a positive charge, the next charge is a negative charge. Now it is placed in a magnetic field. So these are designed to show that it's surrounded in a magnetic field. Now what we observe is that if we bring a test charge, let's say a positive charge, and we place it in this field, it is going to be deflected to the positive strip of this conductor, which means that this charge is positive. So if this charge was an unknown charge, let's say X, and you place it here and it drifts towards this positive, we can tell that the charge has a sign that is a positive. The same, if the X is a negative charge, it will be drift towards the negative strip of the conductor, which means that X has a negative. So with the Hall effect, we can simply dictate a charge the sign of a charge carrier. Now, if we place this, we can see that in the Hall effect experiment, there will be a potential difference that will be created between the two conductors. So I will call this conductor M and conductor N. So the potential difference created here is going to be given as VMN. So that is our potential difference in this experiment. Now also from here to here is a distance of separation of the conductors. Another thing as well that we are going to look at. But what theory we observe here is that when this potential difference is created, there will be a point whereby we see that the electric field force is equal to the magnetic field force. So electric field equals to the magnetic field. So at that point, you are going to see from our previous class, the electric force is given as QE and the magnetic force is given as QV So when these two are equal, you can see that the charge here will cancel out the charge. So what we have is E equal to V B. So our E equal to VB, which we can make V the subject formula. Our V, which is the velocity of the charge, is equal to E all over B. So with this, I can calculate the velocity of the charge simply by getting the electric field and the magnetic field. If I divide them together, I have gotten the velocity of the charge. Now, when we look at this, we have to flash back to the theories involved in electromagnetism and as well your magnetism. So you see that on electric fields, we have that the electric field is equal to V all over D, where this V is called the potential, which is this our potential here, Mn. So the potential between the point M and N. Then D is the distance of separation. So if we should make Vm the subject formula, we cross multiply, one can see that Vmn is equal to Ed. So the potential difference between the points M and N is equal to the electric field times times D. So from here, you can see that we already have the electric field as VB. So we can make the substitution here, and we are going to see that VMN is equal to VB then times times D. So in place of E, we are using VB. So you can see this V is the velocity of the charge, but this capital V is the potential difference. So take note of that, very important. Now also, if we also flash back to our theory of electric field, we have that this velocity, which is called the drift velocity, which is the same as what we have here, is equal to the current all over NQ A. So with this, I can get the drift velocity. So you can plug in everything inside here, and you are going to have that Vmn will be equal to Vd, which is the whole of this now, right? So we have I all over NQA, then times Bd. So we have this. Now, a little arrangement of this formula implies that our Vmn is equal to I, or let's start with 1 all over NQ. Then let me bring my I here, so that the I is multiplying with Bd all over A. So now, this N is the number of charge per unit volume. Then our Q is the charge of the electron. Then we have the area, we have the magnetic field, the current, and the distance. So also, this factor 1 all over NQ is what we call the Hall coefficient factor. So this is the Hall coefficient factor. Sometimes in exam, they can give you this as a constant. So you just make your right substitution, don't need to calculate for it, and start solving. Then this N is the number of charge per per unit volume. So take note of that. That's the number of charge per unit volume. So it should be written as per volume. That is the units per meter cube. So with this, we have been able to analyze the Hall effect experiment. Thank you. Make sure you subscribe to the channel. If you have not subscribed, go to the notification button, click on it, because MikeSword will be giving more videos on electromagnetism, your modern physics, wave thermal physics, and your mathematics as well with your chemistry. Thank you.